Welcome back to Mechanical Engineering Made Simple.
It's great to be here.
I had a bit of a moment this morning. I was driving over that massive suspension bridge, the one I take every day to get to the studio.
Mhm.
And usually I'm just, listening to the radio, drinking my coffee, not thinking about much. But today I found myself gripping the steering wheel a little tighter. I was looking up at those huge cables, the ones as thick as my body, and then looking down at the concrete piers. And instead of thinking, wow, what a marvel of engineering, I was thinking, my God, look at the millions of ways this thing could kill me.
That is a very, very common side effect of reading the material we've covered for today.
I bet.
You start to see the world not as a collection of solid objects, but as a collection of invisible forces all trying to tear those objects apart.
Exactly. It's like I've taken the red pill. Because we aren't just talking about how to build things today, are we? We're talking about the dark side of engineering, the study of failure.
It is the burden of the engineer, in a way. People think engineering is about creation, and it is. Of course it is. But more than that, it's about prediction.
Prediction.
It's the study of limits. How much can a material take before it stretches? How much before it twists? When will it corrode? And, the ultimate question, exactly when and how will it snap?
And that's really the mission for this deep dive. We've gone through 2 absolute tomes of technical literature, specifically looking at stress analysis from one source and failure considerations from another.
2 massive texts, yeah.
And my goal today is to bridge that gap, pun fully intended, between the abstract math, all the Greek letters, the formulas on the page, and the real-world consequences. We're talking about preventing planes from falling out of the sky. We're talking about why a bolt on my lawnmower snaps when I barely feel like I've touched it.
And it is a fascinating journey because whether you are designing a high-pressure jet engine turbine blade or just, building a deck in your backyard, the physics are exactly the same.
It's all the same rules.
Understanding how forces flow through matter, where they concentrate. That's the difference between a working machine and a pile of scrap.
Okay, so let's unpack this. We have to start with the vocabulary, the language of load. If we're going to talk about things breaking, we have to talk about stress and strain.
For fundamentals.
Now, in normal English, if I say I'm under a lot of stress or I'm under a lot of strain, I basically mean the same thing. I mean I need a vacation.
Right.
But in your world, these are totally different concepts, aren't they?
Well, completely different. They are cause and effect. And confusing them is probably the first mistake most people make when they get into this field.
So where do we start? Stress.
Let's start with stress. Imagine you have a bar of steel just hanging from the ceiling, and you attach a weight to the bottom of it. You are pulling on it. That pulling force is the load.
Okay, the weight.
Right. But stress isn't just the load. Stress is the load divided by the area it's acting on.
Right. I saw the formula in the text. It's written as the Greek letter sigma equals P divided by A.
Correct. Sigma is the unit stress. P is the force, the load. And A is the cross-sectional area. Now, why do we do this? Why bother dividing by the area?
I assume it's to make it fair, to, compare apples to apples.
Precisely. That's a perfect way to put it. Think about it this way. If I put 1,000 pounds of force on a massive, thick steel column, like the kind holding up a building.
The column doesn't even notice.
It's negligible. But if I put that same 1,000 pounds of force on a thin piano wire.
Snap. It's gone. Immediate failure.
Right. The force, the P, was the same in both cases, but the result was totally different. So force by itself is actually a bad way to predict failure. Stress normalizes that force. It tells us the intensity of the load.
I love the analogy of the snowshoe versus the stiletto heel.
That is the classic example, isn't it?
Yeah.
You can have a 200-pound person wearing snowshoes walking across soft snow. They don't sink. Why?
Big area.
Because that 200 pounds is distributed over a huge area. The P is 200, but the A is massive. So the pressure on the snow is really low.
But put that same person in a stiletto heel.
And all 200 pounds is focused on a tiny, tiny point. The area A is minuscule. So the stress skyrockets, and the heel just punctures the snow or your hardwood floor.
Right, or my floor. Okay, so stress is the intensity of the force, and you mentioned there are 3 pillars of stress, 3 flavors.
Yes. The way the force is applied matters a lot. First, there's tension. This is pulling. Imagine a tug-of-war rope. You are literally trying to pull the atoms in the rope apart from each other.
Okay, pulling. Got it.
Second is compression. This is the opposite. It's crushing. Think of the concrete pillars holding up that bridge you drove over. Gravity is pushing down on the road, the ground is pushing up, and the pillar is being squeezed in the middle.
Forcing the atoms closer together.
Forcing them closer, yes.
Yeah.
And the third one,
This is the one that always gets me. Shear.
Shear. It's the tricky one. Tension and compression act along the line of the object. Shear acts across it. The best way to think of it is a deck of cards. You put the deck on a table, you put your hand on the top of the deck and slide it forward while the table holds the bottom of the deck still. The cards slide over each other.
That sliding action is shear.
That is shear stress. Scissors work on shear stress. That's why they're sometimes called shears. One blade goes up, one blade goes down, and the paper in the middle experiences a sliding failure. It doesn't stretch, it slices.
Okay, so that stress, that is what we are doing to the material, the cause. Now let's talk about strain. This is the effect.
Yes, strain is the response. It's denoted by the Greek letter epsilon. And technically, it's defined as the deformation per unit length.
Deformation per unit length. So how much it stretched divided by how long it was to start with. Is that it?
That's it exactly. If you have a 10-inch rubber band and you stretch it by 1 inch, the total deformation is 1 inch. The strain is 1 divided by 10, 0.1. It's a dimensionless measure of the geometric change in the material.
So if stress is the cause, the invisible force field inside the metal strain is the effect, the actual physical movement that we can see and measure.
That is a perfect way to visualize it. And for centuries, engineers and scientists, they tried to figure out exactly how these two are related. If I pull twice as hard, does it stretch twice as much?
And the answer is yes. For a while, at least.
For a while, yes. This brings us to the brilliant Robert Hooke and Hooke's law. Back in the 17th century, Hooke discovered that for most structural materials, steel, aluminum, wood, bone even, there is a beautiful linear relationship.
Linear meaning a straight line on a graph.
A perfect straight line. If 100 pounds stretches at 1 millimeter, then 200 pounds stretches at 2 millimeters, 300 pounds, 3 millimeters. It is perfectly predictable. We call this the proportional limit.
And the slope of that line, that magic number that defines the relationship for a given material.
That is the modulus of elasticity. We often call it Young's modulus, or just capital E.
I always struggled with this concept in school. Is E just how strong the material is?
No, and that is a crucial distinction. E is not strength. E is stiffness.
Okay, what's the difference?
Think of a rubber band and a piece of steel wire, both the same size. You can stretch the rubber band easily, right? It has a low modulus, it's flexible, floppy.
Right.
The steel wire is incredibly hard to stretch. It resists deformation. It has a very high modulus. It is stiff. But strength is about when it breaks. You can have a material that is very stiff but breaks easily, like glass.
Oh, okay.
Or a material that is floppy but very hard to break, like a bungee cord. Young's modulus just tells you how much it will stretch for a given load within that elastic region.
Got it. So steel is stiff, rubber is flexible, diamond is incredibly stiff.
Correct. And there's another layer of nuance here that I just find fascinating. Poisson's ratio, the Greek letter nu.
This is the 3D part of the puzzle, right?
It is. Because nothing happens in isolation. When you stretch that rubber band, you are pulling it longer. That's the longitudinal strain. But look closely at the middle of the band. What happens to its width?
It gets skinnier and necks down in the middle.
Exactly. To get longer, it has to get thinner. Nature tends to conserve volume. Poisson's ratio is simply the ratio of that sideways shrinking to the lengthwise stretching. The lateral strain to the longitudinal strain.
I saw in the notes that for steel it's about 0.3 and for concrete it's like 0.1.
Right, which tells us something, doesn't it? It says that steel is much more cooperative in rearranging its shape than concrete is. Concrete just kind of sits there and resists. It doesn't like to get skinny.
Okay, so we're pulling on this bar of steel, we're measuring the stress, we're measuring the strain. We can plot this on a graph. The famous stress-strain diagram.
The biography of the material.
It really looks like a medical chart. It tells you the story of the material's life from beginning to end.
It really does. It tells you everything you need to know about its personality.
Uh-huh.
Let's walk through the life of a piece of, say, structural steel, like the kind in your bridge.
Okay, so we start at zero stress, zero strain. We apply load. We are climbing up that straight line. Hooke's law is in effect.
We are in the elastic range. This is the safe zone for design. The happy place. If you take the load off right now, the steel snaps back to its original shape perfectly. No harm, no foul.
The atoms were just pulled apart slightly, like they were on tiny springs, and then they just sprang back.
Perfect analogy.
Yeah.
But then we hit a point where the line stops being perfectly straight. The proportional limit.
The end of Hooke's law.
Yes. The relationship gets a little fuzzy here, but we are still elastic. We can go a tiny bit further to the elastic limit. This is the absolute point of no return.
The point of no return? That sounds ominous.
It is, because once you cross the elastic limit, you hit the yield point, And this is where the magic or the damage happens. The material yields.
Yields, as in it gives up, it surrenders.
Sort of. It stops acting like a spring and starts acting like taffy or clay. It begins to flow. This is plastic deformation.
Plastic deformation. Permanent.
Permanent. The crystal layers inside the metal are actually sliding over each other. We call them slip planes, and getting stuck in new positions. If you take the load off now, it won't go back to its original length. It is permanently stretched. You have bent the paperclip.
But it hasn't snapped yet, not even close.
No. In fact, steel does something incredible here. After it yields, it actually gets stronger. It's called strain hardening.
How does that work?
As those crystal layers slide and tangle up, they create a mess of dislocations that block further movement. It's like a traffic jam on the atomic level. So you have to pull even harder to get it to stretch more. The curve actually goes up again.
It fights back.
It fights back hard until it hits the peak of the curve, the ultimate tensile strength.
The highest stress it can ever survive.
The absolute maximum. Once you pass that peak, the game is over. The material starts to neck down visibly. You can see it get very thin in one spot. And then POW.
Rupture.
Rupture. The breaking strength. The end of the story.
Now, the distance on that graph, the amount of stretch between that yield point and the final snap seems really, really important.
It is absolutely critical. That amount of plastic deformation defines whether a material is ductile or brittle.
And ductile is the taffy, the stretchy stuff.
Yes. Structural steel, aluminum, copper, gold, they stretch a lot before they break. They give you a warning.
A warning.
If a steel beam in a building is overloaded, it will sag. It will bend visibly. You can see it and say, we need to get out of here.
And brittle.
Brittle is glass, cast iron, ceramics. You pull on them, they stretch a tiny, tiny bit in that elastic range, and then they just shatter. No warning, no sagging, just a sudden catastrophic explosion of energy.
So for a bridge, we definitely want ductile for everything, basically.
For almost everything structural, yes.
Yeah.
We want toughness. And in engineering, toughness has a very specific definition. It's the total area under that stress-strain curve. It's the ability to absorb energy before fracturing.
So it's not just about being strong.
No. A tough material is strong. It takes a lot of force, a high curve, but it's also ductile. It stretches a lot, a long curve. That combination allows it to absorb the energy of a truck hitting a pothole or an earthquake shaking the ground without just snapping.
Okay, so we've got the material science down. We understand the personality of the steel. Now let's look at the shapes we build with it. Beams, shafts, and columns.
The building blocks of the mechanical world.
Let's start with beams. This is bending 101. And there was a concept here that I found really trippy. The neutral axis. It sounds like something from Star Trek, but it's real physics.
It is the magical line. It's very real. Think about a simple beam spanning across a room. You hang a heavy chandelier in the middle. The beam bends down in a smiley face shape.
Right. It sags.
Now think about what the wood or steel fibers are doing inside that beam. The top surface of the beam is getting shorter. It's being crushed together. It's in compression.
Okay.
The bottom surface of the beam is getting longer. It's being pulled apart, stretched. It's in tension.
So if the top is squished and the bottom is stretched, somewhere in the middle, there has to be a place where nothing is happening.
Somewhere in the middle, there is a single layer of fibers that is doing absolutely nothing. It isn't getting shorter and it isn't getting longer. The stress there is zero. That is the neutral axis.
That is wild. You have these huge forces, tension and compression at the top and bottom, and then just dead calm right in the center.
And that single insight leads to perhaps the most famous and useful formula in all of beam design, the flexure formula.
Yes. Sigma equals m times c, all divided by I.
That's the one. Let's decode that.
Okay. Sigma is our old friend, stress. M is the bending moment, which is basically a measure of how hard we are trying to bend the beam.
Correct. And c is the distance from that neutral axis.
So C tells us that the stress gets bigger the farther you get from the center.
Exactly. The top skin and the bottom skin are taking the worst beating. The stress is at its absolute maximum at the outer surfaces.
Okay, that makes sense. And then we have this capital I on the bottom of the fraction, the moment of inertia. Now, honestly, in high school physics, this was the concept that always tripped me up. Is it mass? Is it weight? What is it?
It's neither, really, and that's why it's confusing. Think of I as a measure of geometrical stiffness.
Yeah.
It has nothing to do with the material itself. It's not about how much steel you have.
Yeah.
It's strictly about exactly where that steel is located relative to the neutral axis.
Okay, help me visualize that. I need an analogy.
The best one is a standard 2x4 wooden plank. If you lay it flat on two cinder blocks, the wide weight, like a bridge,
Right.
and you stand in the middle, it bows quite a bit, doesn't it? It's bouncy.
Yeah, I can picture that.
Now take that exact same 2x4, you haven't changed anything about it,
Okay.
but this time you turn it on its side, so it's tall and skinny. Stand on it now.
It's incredibly stiff. It barely moves at all.
Exactly. You haven't changed the material. You haven't changed the mass or the weight. It is the exact same amount of wood, but you change the distribution of the area relative to the axis of bending. By moving the wood vertically, far away from the center, you have exponentially increased I.
And since I is in the denominator of the stress equation, a huge I means a tiny stress.
A tiny stress. And this explains the I-beam. It's not just a letter of the alphabet. It's a genius-level strategy.
It's a strategy to cheat gravity.
It is. You take all the steel out of the middle, near the neutral axis where it's doing almost nothing, and you push it out to the top and bottom flanges, the extremes. You're putting the soldiers on the front lines where the war is being fought.
That makes so much sense now. Okay, so moving from bending to twisting. Torsion. Shafts. Like the drive shaft in a car.
A very common application, yes. Here, we aren't dealing with tension and compression so much as we're dealing with shear. You are twisting the bar. And just like with bending, the distribution of the material matters enormously. Where do you think the stress is in a twisting rod?
Well, based on the beam logic, I'm going to guess it's 0 in the very center, and it's at a maximum on the outside surface.
Spot on. The absolute center of a spinning shaft carries 0 torsional load. It's just along for the ride. The outer skin is doing all the work, experiencing the maximum shear stress.
Which explains why so many drive shafts and axles and even light poles are hollow tubes.
Precisely. Why pay for the heavy, expensive steel in the middle if it isn't doing anything? A hollow tube can handle nearly the same amount of torque as a solid rod of the same diameter, but at a fraction of the weight and cost.
Nature, or I guess engineering, is lazy. Or efficient.
Efficient. Always efficient.
Okay, last one in this section. Columns. This is where things get a little sketchy. Because columns fail in a really weird way. Buckling.
Buckling is terrifying to engineers because it's an instability failure. It's not about strength.
What do you mean by that?
Well, if you have a short, stubby block of steel, like a little cube, you have to literally crush it to make it fail. That takes millions and millions of pounds. But if you take that same steel and make it into a long, skinny rod,
like a yardstick.
Exactly like a yardstick. You push on the ends with just a little force and suddenly, POP, it bows out sideways. It kicks out. You didn't crush the wood. You didn't even get close to the yield strength of the material. It just gave up. It became unstable.
And there's a famous formula for this, right? The Euler formula.
Leonhard Euler.
Ugh.
He figured out that the critical load, the load at which it buckles, depends very, very heavily on the length. In fact, it depends on the length squared in the denominator.
Whoa, squared. So if you double the length of a column, you make it 4 times weaker against buckling.
4 times weaker. It's a huge penalty. And that's why you see all that cross-bracing and scaffolding or radio towers. They are trying to shorten the effective length of the columns to prevent that sudden buckling snap.
The source material also mentions the second formula. It says Euler's formula assumes everything is perfect.
Which, of course, never happens in real life.
Right.
In the real world, the column is never perfectly straight. The load is always a little tiny bit off-center. We call that eccentricity. The secant formula is a much more complex but more realistic formula that accounts for that initial imperfection, that wobble. It's the real-world version of the math that tells you things are going to fail even sooner than the perfect Euler case predicted.
Comforting. Now, speaking of the real world, real parts rarely see just one type of load. This brings us to combined stresses. A real part doesn't just get pulled or just get twisted, it gets everything at once.
Oh, absolutely. Imagine a crankshaft in a high-performance race car. It's spinning at 8,000 RPM. The explosions in the cylinders are banging down on it.
That's bending.
The resistance from the wheels is trying to stop it from spinning.
Yeah, that's torsion.
The whole thing is incredibly hot, so it's trying to expand.
Thermal stress.
Exactly. It's a chaotic storm of forces acting in every direction simultaneously.
So how on earth do we even begin to calculate, will it break, if the forces are pointing in 10 different directions?
We use a clever mathematical technique to find what we call the principal stresses. Basically, we take a tiny imaginary cube of material anywhere inside the part, and we use math, basically trigonometry, to rotate that cube in our minds. We spin it around till we find the one specific angle where the pulling stress, the tension, is at its absolute maximum and the shear stress is 0.
So we're looking for the worst case scenario angle.
We were finding the absolute worst case tension and the worst case shear at that point. And there's a graphical tool for this called Moore's circle.
I saw that. It looks like something from a geometry textbook.
It is, but it's a brilliant way to visualize this complex 3D stress state in 2D. You plot your known stresses on a graph, draw a circle, and the edges of the circle instantly tell you your maximum principal stress and your maximum shear stress. If the circle gets too big and touches the failure line, you're in trouble.
But trouble is subjective, isn't it? This brings us to the theories of failure. I was honestly surprised by this. I thought there was just one rule. If the stress is bigger than the strength, it breaks. But it's not that simple.
No, it's not. Because strength depends on how you attack the material. Is it ductile? Is it brittle? How is it loaded? So we have different theories for different materials and situations.
Okay, let's break down the big three mentioned in the text. First, the maximum stress theory, also called Ranker's theory.
This is the simplest one. It's the weakest link theory. It says, I don't care about the complex combination of stresses. If the pulling force in any one direction hits the breaking point of the material, the whole thing snaps.
And this works for brittle stuff, like glass.
Exactly. Think of a piece of chalk. If you twist it, it doesn't shear flat, it snaps on a clean 45-degree angle. Why? Because that's the angle where the tension was highest. Rankine works great for chalk, glass, and cast iron.
But it's dangerous for steel.
Very dangerous. Steel is ductile. It doesn't care that much about being pulled. It cares about sliding. It fails in shear. So, for steel, ranking might predict you're safe when you're actually about to yield. For steel, a better, more conservative choice is the maximum shear theory, or Guest's theory.
And that one just says that failure happens when those sliding layers, the shear stress, hits its limit.
Correct. It says yielding begins when the maximum shear stress in the part equals the shear stress that would cause yielding in a simple tension test. It's a safer bet for ductile metals.
But then there's the third one, the one the text calls the gold standard, the distortion energy theory, also known as von Mises stress.
Ah, von Mises. This is what every single computer simulation, every finite element analysis program uses today. It's a bit more abstract, but it's incredibly accurate.
Yeah, I struggled with this one. Distortion energy. What does that actually mean?
Okay, think about a balloon filled with water. If you take that balloon and you lower it deep into the ocean, the water pressure is immense, right? It's crushing the balloon from every side equally.
Okay, that's called hydrostatic pressure.
Right. Now, does the balloon change shape?
No. It just gets smaller, it shrinks, but it stays a sphere.
Exactly. It changes the volume, but it does not distort. And it turns out that materials, especially ductile ones, can withstand enormous amounts of hydrostatic pressure without yielding. What breaks things is not the pressure itself, but the distortion, the energy that goes into changing the shape from a sphere to, say, an egg.
So von Mises calculates only that bad energy, the shape-changing energy.
Precisely. It cleverly subtracts out all the safe hydrostatic pressure and calculates only the energy stored in the material from being distorted. And it says the material will yield when that distortion energy hits a critical limit. It is the most accurate predictor we have for when steel will actually yield.
So if I see one of those colorful engineering stress maps on a computer, the red danger zone is showing me high von Mises stress.
99% of the time, yes. That's what you're looking at.
Before we leave this, we have to talk about stress concentration. The text used a force flow analogy that really clicked for me.
This is one of the most important and often overlooked concepts in design. We tend to think stress is spread out evenly, like butter on toast. But it's not. Stress flows more like water in a river.
So if the river is wide and straight and smooth, the water is calm, it flows evenly.
But what happens if you stick a giant sharp-edged boulder in the middle of that river?
The water has to rush around it, it speeds up, it gets all turbulent right at the edges of the rock.
Exactly. In a material, that boulder is a hole, or a sharp notch, or a sudden change in diameter. The lines of force can't go through the hole, so they have to crowd together to get around the edges.
And that crowding means the local stress is higher right there.
Much, much higher. We have a term for it. The stress concentration factor, or K sub T. For a nice smooth plate in tension, the stress is, let's say, 10,000 psi. If you drill a simple circular hole in the middle of that plate,
the stress goes up.
The stress right at the top and bottom edge of that hole jumps to 30,000 psi.
It triples, just because of a simple hole.
It triples. And this is why engineers are absolutely obsessed with fillets. Those nice, smooth, rounded corners you see on machine parts. Sharp 90-degree corners are death. They are massive stress concentrators. A rounded corner lets that river of force flow smoothly around the bend instead of crashing into a wall.
That is a perfect segue into our next section, because those little stress concentrations, those little notches and scratches, are usually where the silent killer begins its work. Fatigue.
Fatigue, yes. This is the big one. This accounts for the vast, vast majority of mechanical failures in history. And it is, in many ways, the most frightening type of failure because it feels like a betrayal by the material.
Okay, I have to stop you there because this sounds like a complete contradiction. We just spent 20 minutes establishing that steel has a yield strength and an ultimate strength. The whole point of the stress strain curve is that if I stay below those numbers, if I'm in the safe elastic zone, the math says the part shouldn't break. Ever.
The static math says that. The math for a one-time pull.
So you're telling me I can follow all the rules, I can design my part so the stress is way, way down in the safe zone where Hooke's law says everything just springs back perfectly, and the part will still fail. That feels like the material is cheating.
It feels that way, doesn't it?
Yeah.
It's the difference between lifting a heavy box one time and bending a simple paperclip back and forth 100 times. The force to bend the paperclip is tiny. You aren't overloading it in the traditional sense at all. But what are you doing to the crystal structure every time you bend it?
I'm wiggling it. I'm working it back and forth.
You are introducing microscopic cumulative damage. Every single time you bend it, a tiny dislocation, a flaw in the crystal lattice, moves a little bit. You do it once, it's fine. 10 times, it's fine. But a million times, those tiny dislocations start to bunch up. They form a micro crack. And then, on cycle number 1, 1,000,001, snap.
And this happens well below the yield point.
Oh, way below. It can happen at half the yield strength or even less, depending on the conditions. That is fatigue. Failure under a fluctuating or cyclic load.
We visualize this with something called the SN curve.
The SN curve. It's the cornerstone of fatigue analysis. You plot stress, the S, on the vertical axis against the number of cycles to failure, the N, on the horizontal axis, which is usually a logarithmic scale.
And it slopes down, right? Higher stress, fewer cycles.
Generally, yes. The lower the stress you apply in each cycle, the more cycles the part can survive. It's a downward sloping curve.
But there's a really weird and important quirk here, especially between steel and aluminum, something called the endurance limit.
This is one of the miracle properties of steel, and one of the reasons we build bridges and engine blocks out of it. For steel and other ferrous alloys, that downward SN curve eventually flattens out. It becomes horizontal. It hits a floor.
A floor.
We call that the endurance limit or fatigue limit. It means if you design your part so the cyclic stress is below that floor, the steel will theoretically last forever. Infinite life. You can cycle it 1 billion, 1 trillion times, and it just won't fail from fatigue.
That's incredibly reassuring, but not for aluminum.
Aluminum is different. Non-ferrous metals like aluminum, magnesium, copper. Their SN curve never flattens out. It just keeps going down and down and down, getting closer and closer to zero.
So you're saying aluminum will eventually fail, no matter how gentle you are with it?
Given enough cycles, yes. Even at very tiny stress levels, there is no infinite life stress for aluminum. And that is why aircraft, which are mostly made of aluminum, have very strict mandatory lifespans. We count the cycles.
Every takeoff and landing is a cycle.
It's a major pressurization cycle on the fuselage, yes. When a plane hits its designated cycle limit, it's done. We have to retire it or do a major structural overhaul because we know the fatigue cracks are statistically inevitable.
That is slightly terrifying to think about next time I'm in a window seat looking at the wing flexing.
It shouldn't be terrifying. It should be reassuring. It means we know the limit, we account for it, and we apply massive safety factors to stop well before we get there.
Okay. Now, there are a lot of factors that can make fatigue even worse. The text highlighted surface finish as a big one.
Oh, a huge factor. Remember our stress concentration discussion?
Yeah, the notches and holes.
Well, if you have a rough surface finish, from machining or grinding or even just scratches, each one of those tiny scratches is a microscopic notch, a tiny stress concentrator. It's a pre-made starting point for a fatigue crack.
So polishing a critical part isn't just for making it look pretty.
Not at all. It's for survival. A polished mirror finish will remove all those potential starter cracks. It can easily double or triple the fatigue life of a component.
What about the size of the part? The text mentioned a size effect.
This is a weird statistical reality that trips a lot of people up. All other things being equal, bigger parts are weaker in fatigue than small parts.
Wait, weaker? That seems backwards.
I know. If I make a small pencil-sized steel rod and test it in the lab, it might last 1 million cycles at a certain stress. If I build a giant propeller shaft out of the exact same steel, It might fail at only 500,000 cycles at that same stress level.
But why?
It's a game of statistics and volume. A bigger part simply has more atoms. More volume means a higher statistical probability that there is a microscopic flaw somewhere in that metal from the manufacturing process. A tiny piece of slag, an inclusion, a microscopic void. The bigger the haystack, the more likely you are to find the one needle that will start the crack.
And of course, the environment. We have to talk about corrosion.
Corrosion is a killer. If you are cycling a part in a salty or acidic environment, the corrosion creates pits in the surface. Each one of those pits is a perfect, sharp-bottomed stress razor. It's like drilling thousands of tiny holes all over your part. It accelerates the fatigue process dramatically. A devastating 1-2 punch.
Okay, so we've got fatigue, which is the process of a crack starting and growing slowly. But what happens when that crack gets big enough? This brings us to Section 5, fracture mechanics. The text calls this a paradigm shift.
It was a massive, massive shift in engineering thinking, really starting around World War II and solidifying in the 50s and 60s. Before this, the design philosophy was based on the stress-strain curve. We assumed materials were perfect, continuous solids.
Right.
Fracture mechanics starts with a much darker, more realistic assumption. It says, the material is already cracked. There are already flaws from manufacturing. We can't see them, but they're there. Now what?
That completely changes the question from, will it break, to how fast is the existing crack growing and when does it become critical?
Precisely. We stop talking about average stress, and we start talking about the stress at the tip of a crack. And we introduce a new variable. We talked about K sub D before, the stress concentration factor.
Yeah.
Now we talk about capital K, the stress intensity factor.
The symbols are confusingly similar.
They are, which is unfortunate, but the concept is very different. K describes the intensity of the stress field right at the sharp tip of a crack.
Right.
And the basic formula for it has a really scary term in it. It's that K is proportional to the stress times the square root of A.
And A is the length of the crack.
Yes. The square root of the crack length. This is huge. This means that as the crack grows, as A gets bigger, the stress intensity K gets bigger. And as K gets bigger, it drives the crack to grow even faster, which makes it even bigger still.
It's a runaway positive feedback loop.
It is an exponential runaway process. A crack might grow at a microscopic stable rate for years, for 99% of the part's life. Then, as it gets longer, it starts growing inches per week, then feet per second.
And there's a cliff edge. A point of no return, fracture toughness.
K sub I. That is the cliff edge. K sub I is a fundamental property of a material, just like yield strength. It's a measure of its resistance to a crack running wild. If the stress intensity factor K at the tip of your crack hits that critical value, K sub I, game over. The crack becomes unstable.
Unstable meaning?
Meaning it no longer needs any more cyclic load to grow. It has stored enough strain energy to tear itself apart. It unzips through the material, literally at the speed of sound in that metal. That's when the wing falls off the plane. That's when the ship splits in two in a cold sea. It happens faster than you can blink.
So how do we design for this? We can't make everything perfect. The text mentions a philosophy called leak before break.
This is a brilliant and life-saving design philosophy, especially for things like pressure vessels, pipelines, rocket fuel tanks.
So how does it work?
You choose a material with a very high fracture toughness, and you design the wall thickness such that the critical crack length needed for that final fast fracture is larger than the wall thickness of the vessel.
Okay, translate that for me.
It means you design it so the crack will have to grow all the way through the wall and cause a leak before it gets long enough to cause the whole tank to explode.
So the leak is the warning alarm, the puddle on the floor.
The leak is the alarm. Exactly.
Mm-hmm.
If you see a jet of fluid shooting out, you shut down the system. It's a failure, yes, but it's a safe, detectable failure. If you don't have a leak before break design, your first and only warning is the catastrophic explosion.
I think I prefer the puddle.
You all prefer the puddle.
Moving on, there are other slower ways for things to fail. Section 6 talks about creep. This sounds like a slow-motion horror movie.
It is slow motion. Creep is the tendency of a material to slowly move or deform permanently over time when it's under a constant load.
Wait, the load doesn't change, but the part just keeps stretching by itself?
Yes. Usually this is a high-temperature phenomenon. The classic example is a turbine blade in a jet engine.
Okay.
It's spinning incredibly fast, so centrifugal force is constantly pulling on it. And it's sitting in a gas stream that's, say, 2,000 degrees Fahrenheit. Even though the stress from the spinning is well within the safe zone, the atoms are vibrating so violently from the heat that they can slowly slide past each other over hundreds of hours.
So the blade physically gets longer.
It grows. like a glacier moving. And if you don't account for this in your design, the blade tip will eventually grow so long that it hits the outer casing of the engine. And that's a very bad day.
The text mentions 3 stages of creep.
Right. There's primary creep, where the rate of stretching starts fast and then slows down as the material strain hardens a bit. Then there's secondary, or steady-state creep. This is the long, slow, constant rate stretching where the part spends most of its life. And finally, there's tertiary creep.
The end game.
The end game. The material starts to develop voids and microcracks internally, the stretching accelerates rapidly, and then rupture.
And different materials have very different temperature thresholds for this.
Hugely different. A soft metal-like lead will creep significantly at room temperature. That's why ancient lead roofs on European cathedrals have often sagged and flowed downhill over the centuries.
Wow.
Steel needs to get up around 650 or 700 degrees Fahrenheit to start creeping noticeably. The nickel-based superalloys we use in jet engines can resist creep up to 2,000 degrees or more.
And what happens when you mix creep and fatigue? Like in that turbine blade, which is hot and vibrating.
You get a nightmare. It's a synergistic effect where they make each other worse. The vibration from fatigue creates cracks. The high temperature from creep causes voids to form at the grain boundaries. The voids then link up, giving the fatigue cracks an easy path to travel. It drastically reduces the lifespan of the part compared to either one acting alone.
Let's talk more about the environment, Section 7. We touched on corrosion, but there's a specific type of failure here that honestly just terrified me. Fretting.
Fretting, the hidden enemy. It's so insidious because it happens in places you think are solid and safe, like a bolted or riveted joint.
So nothing is visibly moving.
Nothing you can see. But imagine 2 plates bolted together in a machine that vibrates. They're clamped tight. But because of the vibration, there is microscopic relative motion between the 2 surfaces. They're slipping back and forth by just a few micrometers.
And that tiny little rubbing motion is the problem.
It's a huge problem. It acts like a submicroscopic sandpaper. It rubs off the protective oxide layer on the metal, exposing fresh metal, which then instantly oxidizes, and that gets rubbed off. It grinds the metal into a very fine powder, usually a black or reddish-brown dust. In the aviation world, we call it cocoa.
And that dust.
That cocoa is abrasive, and the process creates tiny pits in the surface. And what are pits?
Stress concentrations.
Exactly, which then become the initiation sites for fatigue cracks. And the truly scary part is, this is all happening inside the joint where you can't see it. The mechanic looks at the bolt head, and it looks perfectly fine. But inside, the joint is bleeding metal dust and growing a crack that's about to cause failure.
The other environmental killer mentioned was stress corrosion cracking, or SCC. This felt like a chemical detective story.
It is. SCC is the perfect storm of material failure. You need 3 things to happen at the same time. If you only have 2, you're fine.
Okay, what's the deadly trio?
First, you need a susceptible material. Second, you need a specific, often seemingly harmless corrosive environment. And third, you need a sustained tensile stress.
If you have all 3,
disaster. A sudden, brittle-like failure in a normally ductile material. The classic historical example is the season cracking of brass ammunition cartridges used by the British Army in India.
Okay.
They store their ammunition in horse stables. The horse urine in the stables create ammonia fumes in the air. Well, it turns out that brass is highly susceptible to ammonia.
So that's 2. Susceptible brass, corrosive ammonia.
And the third, the bullet casing was under a constant tensile stress from the manufacturing process, where it was crimped around the bullet.
The perfect storm.
The perfect storm. The cartridges would just split and crack open while sitting inertly in the boxes. The chemical attacks the grain boundaries in the metal, weakening them, and the stress just pulls them apart. It can cause a stainless steel pipe in a chemical plant to shatter like glass if just a trace amount of the wrong chloride is present.
We've covered a lot of ways things can die today, which brings us to our last section, failure analysis. This is the CSI portion of the show.
It is forensics for machines. When a bridge falls or a plane crashes, the NTSB or an engineering team goes in. We don't just ask, did it break? We ask, what was the failure mode? And more importantly, what was the root cause?
What's the difference between those 2?
The failure mode is the physical process. It failed by high cycle fatigue, or it failed by ductile overload. The root cause is the human error behind it. It failed by fatigue because the designer specified a sharp corner in a high-stress area, or because the mechanic used the wrong bolt.
And you can tell all that just by looking at the broken pieces.
The fracture surface tells the truth. It's the black box recorder of the failure. We look for things like beach marks.
Beach marks, like at the ocean.
Exactly. In fatigue, the crack grows a little bit with each cycle or block of cycles. Every time the machine stops and starts, it can leave a tiny curved ridge on the crack face. They look just like the ripples in the sand on a beach, or like tree rings. By looking at them under a microscope, we can literally see the crack's history and tell how long it was growing.
This crack started 3 months ago, right here at this scratch.
Exactly. If the surface is dull and fibrous with a lot of distortion, it was a ductile overload. It was ripped apart slowly. If it's shiny and granular and flat, it was a sudden brittle fracture. It snapped cleanly. The evidence is always there.
And the goal of all this isn't just to assign blame for a lawsuit.
No, not at all. The primary goal is retrospective design. Every time something fails, we learn a profound lesson. We rewrite the textbooks. We update the building codes and design standards. We change the safety factors. The formulas we discussed today, Euler, von Mises, all of fracture mechanics, many of them were refined or even created because of past disasters that forced us to understand why they happened.
That is a very sobering thought. The engineering codebook is written in blood.
In many ways it is, but it is also hopeful. Because we learn. We don't make the same mistake twice, or at least we try very, very hard not to.
You know, we started this deep dive talking about a bridge and my anxiety about driving over it this morning, but honestly, after unpacking all this, after staring into the abyss of failure for an hour, I think I actually feel better.
Why is that? That seems counterintuitive.
Because I realize it's not magic. It's not just luck holding that bridge up. It's math. It's testing. It's a deep, obsessive, and honestly humbling understanding of stress, fatigue, fracture, and creep. It's knowing all the ways it can fail that allows us to build it so it won't.
That's it. Engineering is a battle against the elements, against time, and against the fundamental forces of nature. And by understanding the enemy, by studying and respecting the failure modes, we can win that battle. We can build a safer, more reliable world.
So what does this all mean for you, the listener? Well, next time you are on a plane, or mowing the lawn, or just crossing that bridge, take a second to look at the metal. Think about the invisible war going on inside the atomic lattice, the constant tug-of-war of stress, the slow, creeping glacier of high temperature, the silent, cumulative memory of fatigue counting every single vibration. And appreciate that someone, somewhere, did the math to make sure that working machine didn't become a pile of scrap.
Well said. A deep respect for the materials.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.